All right, welcome to The Explainer. Today we're diving into an idea that is, well, it's pretty mind-bending. What if the code of life itself, I'm talking about the information inside your DNA, could generate its own gravity?
Yeah, you heard that right. We're going to dive into a hypothesis that tries to connect the most massive forces in the entire cosmos with the tiniest building blocks of life. It's a concept that, and this is no exaggeration, could completely upend some of the most basic rules of physics.
So, where does a story like this even begin? Well, it doesn't start here on Earth. It actually starts out there, in the vast, seemingly empty dust between the planets, with a really cool old idea called panspermia. Okay, so panspermia, it's not a new idea, not by a long shot. It's this theory that the basic building blocks of life are just everywhere, all over the universe, and that life here on Earth might have gotten its start from ingredients that basically hitched a ride from another planet. You can think of it like a cosmic delivery service for the essentials of biology. But wait a minute. How could something as delicate as DNA possibly survive a trip through space? I mean, it's brutal out there. Well, the hypothesis we're looking at today suggests that nature found a way. It built its own tiny little spacecrafts, these super tough biological shells that protect the genetic code. And this creates a kind of biodust that, in theory, could be just sitting there, waiting for us in the soil of the moon, or maybe even Mars. Okay, so let's say this biodust is real, and it's out there. What in the world does that have to do with gravity? Well, to connect those dots, we've got to take a step back and look at the fundamental rulebook for the entire universe, none other than Einstein's theory of general relativity. It's been our go-to guide for over 100 years. All right, don't let the symbols freak you out. In really, really simple terms, this famous equation just says that the amount of mass and energy in one spot tells spacetime how to bend and curve around it. The more stuff you have, the more gravity you get. Pretty straightforward, right?
But what if that's not the whole story? What if something's missing from that equation? This is where things get really interesting, because a new hypothesis is suggesting a pretty radical addition to one of the most foundational rules in all of physics.
So here it is. The idea is to tack on a whole new term to Einstein's equation. That little T info you see there, that represents, well, information. The theory is that it's not just mass and energy that create gravity, but also the sheer complexity of biological molecules. Scientists use something called sequence entropy to measure how complex and, unpredictable the code in a DNA strand is. So the more complex that code is, the more information it's packing, and here's the kicker, the more it might actually be adding to gravity.
Right, so what does that actually mean? It means that information itself, when it's physically written into a molecule like DNA, might have its own tiny but very real gravitational pull, the weight of information. This is the perfect analogy for it. It's not about the physical weight of the paper and ink in the books. We're talking about the stories written on those pages. In the same way, we're not talking about the physical mass of the DNA molecule. We're talking about the immense, mind-boggling complexity of the genetic code that's written inside it. This hypothesis suggests that all that structured information could be a source of gravity completely on its own. So this really breaks it down nicely. You've got two completely different proposed sources for gravity. On one side, you have standard gravity, the one we all learned about in school. It comes from mass and energy, basically the weight of things. But on the other side, you have this brand new, totally speculative idea of an information pressure, which would come from the complexity of things. Two different sources for the same fundamental force.
Okay, now before we all get too excited, let's put this into perspective. The effect they're predicting is, well, it's unbelievably small. Just look at that number. We are talking about an acceleration so tiny, it would be like trying to measure the gravitational pull of one single human cell from across the room. It is almost impossibly faint.
So that brings us to the billion-dollar question. How do you weigh a whisper? I mean, how could you possibly detect a force that small without it just getting completely lost in all the other noise and vibrations of the world?
Well, the scientists who came up with this have a very smart, very careful, step-by-step plan. And what's really cool is that the whole thing is designed to be falsified. That means it's set up to be proven wrong as fast and as cheaply as possible if the effect just isn't real. You start small, in the lab. Then you test it on the ground. And only if you see something promising do you even start to think about launching it into space. And check out the toolkit for this. The instruments you'd need for this job are just incredible. To hear a whisper this faint, scientists would have to use some of the most sensitive gadgets ever built. We're talking about balances so delicate they can feel the push from a single particle of light, or using lasers to float tiny little spheres in a vacuum to measure the slightest nudge. I mean, every single one of these tools is pushing the absolute limits of what humanity is capable of measuring. It's amazing stuff.
But hang on, here's a really important question. If this effect is actually real, is there something special about life? Does it have to be biological information, or would any old complex information do the trick? To figure that out, you need a really clever control for your experiment. And here's how they do it. You'd run 2 experiments at the exact same time, side by side. In one, you use actual DNA. In the other, you use some synthetic stuff, like a polymer, but you encode it with random data that has the exact same amount of complexity, the same information density. So by comparing what happens to both, you can figure out if this weird new gravity is something unique to the code of life, or if it's just a general property of any complex information. Okay, but what if they do all this? Build these incredible machines, run these super careful experiments, and find absolutely nothing. No new force, no gravity from information, just silence. You might think that's a failure, but it's actually fascinating. You see, in science, getting a no for an answer isn't a failure at all. It's actually new knowledge. A negative result or a null result is still an incredibly valuable discovery. Think about it. Proving an idea wrong is a huge win for science. It helps us draw the map of reality more accurately. If this information, gravity, doesn't exist, then these experiments will set the most precise limits ever on a force like this. It would tell us that Einstein's theory is rock solid, down to an unbelievable new level of precision. It helps us understand the universe by showing us where the dead ends are. So, after all that, what's the big takeaway? Well, honestly, it's not really about whether this new force exists or not. It's about the scientific process itself. It's about having the guts to ask these huge, bold, even kind of crazy-sounding questions, and then having the discipline and the rigor to actually design an experiment that could give you an answer. Really, this whole thing is just a fantastic example of pushing the boundaries. This is how science moves forward. You take a seemingly impossible idea, you figure out what tiny, faint signature it might leave in the world, and then you go out and build a machine sensitive enough to actually listen for that whisper. And that's really the thought I want to leave you with. Whether this crazy idea turns out to be right or wrong, the search itself pushes our technology and our understanding forward. And it just makes you wonder, what other huge secrets about our universe are hiding right in front of us, just waiting for someone to ask a bold enough question and build a tool sharp enough to find the answer?